Hey, Mr. Nagy's Physics 11 class, and this will be kind of our last lesson on our first dynamics unit on forces in particular is what we're looking at. And I remind you that we started this whole unit talking especially about Newton's laws, and a lot of our focus so far has been on Newton's first and second laws, the laws of motion. The idea that an object in motion will remain in motion unless acted upon by an outside unbalanced force, and when acted upon by a force, an object will accelerate in the direction of the force. That's kind of Newton's second law right there. Tough to handle, tough to get these things because we saw, I think I showed a little video in class about incorrect laws of motion. Our intuition is very often different than what Newton says. The whole idea of acceleration is difficult. It was difficult studying kinematics. It's still difficult. You just can't see acceleration. And our mindset all too often is going fast means accelerating. So I keep trying to break us of some of those intuitive feelings for what physics is all about. This is not going to be much easier, but it can be interesting. So let's get into Newton's third law. We haven't touched on it much. We wrote this down. I took this right off of our first day's notes from Newton's laws. When acted upon by an outside unbalanced force, the object being acted upon will exert a force equal in magnitude and in the opposite direction. So why have I got this picture here? Some lady sitting on a cart being pulled by a donkey. There's this legend, this tale of a donkey that could talk, right? I don't know if this guy can talk here. But he says, hey, I'm not going to pull you along here, lady, because if I apply a force to pull you forward, you're just going to apply a force to pull me backwards, and ultimately I'm not going to get anywhere. So I'm just going to sit here doing nothing. So, you know, that might be a feel for what Newton's third law is all about, but it's wrong. And what's wrong about it is considering the objects being acted upon. There are two objects in this situation. There's the lady in the cart and there's a donkey. They are joined together by, what would it be, a harness or something like that here, some kind of a pole that's attaching the cart to the donkey with the harness, I guess. There are forces acting through that, and that's what we're going to look at with respect to Newton's third law. So if I took a look at the lady alone, and being less than artistic, what's she wearing? She's wearing purple. So here's the lady here. What will be acting on the lady? And that's the lady in the cart and everything else. And I'm drawing it simply. And I touched on this briefly in class. This would be called a free body diagram, FBD, free body diagram. We're going to look at these a lot here, Physics 11, Physics 12. I'm going to constantly be stressing, draw your free body diagram, which just means draw the object very simply and label the forces acting on the object. And you'll say, well, there's gravity and a normal force. And you know what? That's absolutely true. And for neatness and clarity, since our motion that we're observing here is a horizontal motion back and forth, I don't want to worry about the vertical. So I'm going to just get rid of some of that stuff there. The vertical forces, and just concern myself with what's happening horizontally on the horizon. So you bet that the donkey and the pole that's attaching there is going to exert a force on the lady. She's got some mass, the lady in the cart, and there's probably a little bit of friction between the wheels and the ground and so on. So if there is an unbalanced force, a net force, initially she will accelerate. Okay, this is what she's counting on to get going. What's happening to the donkey, right? Why would the donkey, and let's see, we've got a brownish color. Here's the donkey right here. Okay, so you betcha what we're saying here is this force here, according to Newton's third law, is going to pull back on the donkey. But what's pushing forward on the donkey? Well, what's going to be pushing forward is friction between the donkey's four hooves and the ground, right? Opposing motion. When the donkey pushes back on the ground's going to push forward on the donkey, and the donkey can, adjust how much force he pushes back on the ground with. So there's the pole that attaches him. So this is the force of the cart on the donkey pulling back, and this is the force of we'll put it as the donkey on the cart pulling forward, right? This is the force of the ground, okay? Really, friction on the donkey. And if that's greater than that, then the donkey also has a net force forward and will accelerate. And in fact, it's all going to move together. You can look at this, and the donkey's not suddenly going to be way over here and the lady over here. They've got to move together. This is a non-stretchable pole that attaches the donkey's harness to the cart. So let's take a look at a situation like this. Let's say I got a couple of masses, and what we're doing now is we want to verify mathematically that this all works out. You know, it may have made sense here what I drew, right? With my free body diagrams, and hopefully it makes sense. But you know, it's physics, and we need sort of more of a qualitative analysis, a quantitative analysis than just drawing a few arrows on some masses. So here we got, instead of joining two masses with a pole, we're going to apply a pushing force to two masses. Let's say we got 10 kilograms and we got 5 kilograms, and we're able to apply a force of 50 newtons on these two masses. So what's going to happen? Well, whether I've got two masses like this, I may as well just have one big 15 kilogram mass. And by the way, we're going to say there's no friction here. We're going to start in the simplest case. So this would be, and this is the way I will usually label this, APP for applied. I'm applying a force. So again, subscripts, we can choose them, but let's make them have some sense to them. APP for applied. This is my applied force to these masses. Mass 1 and mass 2. It doesn't mean 1 kilogram and 2. I said they're 5 and 10. It's just identifiers. The subscripts are just a way of identifying. Would it make any difference if I applied this 50 Newton force to a 15 kilogram mass? Well, I hope you can see that no, it wouldn't. In fact, in engineering sort of lingo that we're using here in physics class very often, we would call this a system of objects. Okay? We see this a fair bit. We talk about, whoops, let's go yellow for my highlighter here. Systems of objects. When things have to move together, when things work together, a bicycle is a system where your gears and your pedals and everything else works together. In the school, we have mechanical systems, and the mechanical just means moving. Systems might be your heating system, where you have fans and air conditioning devices and heating devices that all work together to keep the place comfortable. You have electrical systems. You have also in your mechanical systems might be your plumbing systems that all need to work together to make things comfortable for the people inside. So, systems is not some fancy word. System is just a whole bunch of things that work together. These two things work together. If I apply a force there, the 10 kilograms not going to move up or down or left or right. Everything's going to move that way, we would assume. Absence of friction. No friction is what I want to write there. They act as if they are one big object. So I could figure out, and I might put a heading here, system. Okay, what's the acceleration net? Net just means actual of the system. Well, by Newton's law, it's going to be the net force on the system divided by the mass total of the system. TOT for total. This would be like my free body diagram, drawing it even simpler, right? There we go. I got no friction. There's my net force. And my mass is 15 newtons, so the acceleration is going to be mass is 15 kilograms. 50 newtons over 15 kilograms, and that's going to be 3.33 meters per second squared. That's the net acceleration of the system. Now, I've got a 10 kilogram mass right here now, and it's accelerating at 3.3 meters per second. Everything has to accelerate at that rate. So if I considered just that, so I'll draw over here my 10 kilogram box. Would have left myself a little bit of room. I might ask, what's the force necessary? And it's actually accelerating at 3.3 meters per second squared, or 3.33, 2 decimal places. Let's see, F equals ma. To accelerate a 10 kilogram box at 3.3, I need 10 times 3.3. I only need a 33 Newton force. And yet, I've applied a 50 Newton force back here. Why does it seem like there's only a 33 Newton? Well, the force that the 5 kilogram object pushes the 10 kilogram object with would be 33 Newtons. And for every action and equal and opposite reaction, how about the 5 kilogram object? It's got 50 Newtons, and yet it's accelerating as if there was only, let's do it this color here, as if there was only, how many Newtons? Well, if I'm pushing back, whoops, let me change colors here. Pushing back here with 33 Newtons, but I've got a forward force here of 50 Newtons. My net force, this was 5 kilograms, by the way. My net force would be 50 minus 33 is 17 Newtons. And the acceleration then would be F over m. And I would get 17 over 5, and that's pretty darn close to 3.3, 3.2 something, 3.4, but it's just rounding differences there, meters per second squared. So you can see, I guess what I'm showing here is the idea that this 33 Newton force here is equal and opposite to the 33 Newton force here. Let's consider another situation like this. These two blocks kind of situation here. I've got a couple of blocks attached by a string. Instead of pushing against one another like we had here, we'll also have this be frictionless. Okay, and let's give some masses. So this is going to be, block B is going to be, let's go with 20 kilograms, and this one here will make 10 kilograms. And out here we'll apply a force, so F applied is equal to, let's make it 75 Newtons. And what's going to happen? So how we would analyze this, and the question we might ask is, what's the tension in this string, string 2? And here's a symbol I might use, F for force. Okay, the word we're going to use here is tension. You're going to see that an awful lot. But tension is just a way of applying a force through a flexible object, not a flexible, an object like a rope or a chain or a string or something like that, or even a solid object like my hockey stick in the classroom. Okay, when I apply a pulling force on something, then the object is said to be in tension. So here I'm going to say, what's Ft2, meaning the force of tension in string 2. The force of tension in string 1 is going to be 75 Newtons. That's what I'm pulling this whole system with. So this is how you analyze these things. First, and I highly recommend, in fact I insist, that you use exactly this method. What's the system going to do? Okay, so put a little heading. This is my system. These things are going to move together, right? The strings attaching them, they all have to move together as a system. The net acceleration of the system is equal to the net force on the system divided by the total mass of the system, same as I wrote before. What's the net force on the system? If I did a free body diagram of the system, I draw it all that stuff there is that blue dot. I got 30 kilograms. And the only thing I've got acting on them, an outside unbalanced force, string 2 is not outside, it's contained within the system, is this 75 Newtons. So the acceleration is going to be the 75 Newton force divided by the 30 kilogram mass, and that's going to be 2.5 meters per second squared. So everything here is accelerating at 2.5 meters per second squared. Now, if I want to find the tension that's acting within the system, So I'm going to look at objects within the system. The tension is pulling forward on that and pulling backwards on that block. Let's take a look at this block right here. Okay, the 20 kilogram block, I'll draw that right here. Look at object in the system being acted upon. Pardon my, this is just too sloppy. Let me just. Look at object. I want you to have this in your notes, so you need to be able to read it. Within the system, being acted upon by the force in question. So again, here's my, I could look at either of these things. If I looked at my 20 kilogram block right here, the only thing I've got acting on that is tension. Now I know my 20 kilogram block is accelerating at 2.5 meters per second squared. Everything was. So looking just at this, the net force is equal to the tension, and the net force is the mass times the net acceleration. It's 20 kilograms, it's accelerating at 2.5, so the net force on this would be 20 times 2.5 is 50 newtons. That would be the tension in the rope. Net force is equal to tension. Really quickly, and you wouldn't normally you could leave it there if you were asked to find the tension. That's it. Let's look at block A back here, the 10 kilogram block. What have we got acting on it? Okay, so this is just an alternate type thing I'm looking at. Well, I've got the applied force here, and that was 75 newtons. And I've got Ft here. And so let's say I want to find Ft in this case. I do know I've got an acceleration of 2.5 meters per second squared. That would be my net acceleration. So in analyzing this diagram, let me move this thing out of the way or even cut this thing. In analyzing this situation, I would say that my net force is equal to that force, the applied force, minus the force of tension, because this must be bigger than this because it's accelerating to the right. F applied minus Ft. I'm looking to solve for Ft, so I'm going to add Ft to both sides. Plus Ft, and negative Ft plus Ft would be 0. And I'm adding Ft to that side, so I get Ft is equal, plus F net equals F applied. So Ft is equal to, and so I'm going to subtract F net from both sides. Just doing the algebra here for you. F net minus F net is 0, so F applied minus F net. Hopefully you can do that with a little less work than I just showed, but so what's the applied force? Well, that was 75. What's the net force? Well, that's going to be the mass times the net acceleration. I know the mass and I know the net acceleration. So 75 minus, this thing was, what was it, 10, right? 10. And the net acceleration was 2.5. So it's 75 minus 25. So that's 50 newtons, which is exactly the same as what I got there, which I would have expected. So for every action, an equal and opposite reaction kind of verifies that. We'll look at more examples, something like the Atwood's machine in class.